What's homework for?
Practice.
Practice? Okay.
Yeah.
It's also graded though. What you have to do is one of those unfortunate things about college is that if it's not a graded assignment, most people won't do it. Which isn't even really a criticism of the quality of student. Like, life is full of things, people get busy, right? So good students frequently don't need homework. And mediocre students frequently do, but don't care. But maybe don't have time. Bad students need it, but don't care and don't do it, so it doesn't matter. So you put it out there. But the reason why I ask is because when I was building the course, the homework was there as effective, like not grade padding, but as a thing that should be easy for everyone to do really well, right? Because you have a week to do it, you have all of your resources and materials immediately in front of you, you don't have to submit it right away, right? But at the same time, some people are doing poorly on the homework, and so I am trying to decide if I'm going to enable multiple attempts on the homework.
Yeah, you should.
But see, and I knew that there would probably be a positive reaction to that. But once again, does that then therefore defeat the purpose of the homework of enforcing you to actually cover the material to learn it? If you know you can just keep doing it, are you going to actually do the work to find the right answer, or just kind of shortchange it, guess on a few things, and then go back and change? Because the questions aren't going to change.
If they could, that would solve it.
Yeah, exactly. If it's just a totally different set of homework. But
You can open it twice, so once I finish it, and then the second time to.
yeah,
I was really bad.
Figure out what I did.
But I'm taking another Chem class with this, and so I was like reviewing all the other Chem stuff, because they're like a week ahead of this Chem course, and I was totally confused.
between their stuff and our stuff? Because the information should be pretty much
Fairly
the
the same, but
Right.
the
ideal gas law isn't going to change.
yeah, it was
Right.
I wanted to say the something A radius.
The atomic radius?
Yes.
Okay.
So like I did my research, there was a video online for that other class. I watched it and it was explaining it backwards, so I got the answers wrong on our end.
You should drop the other class.
No.
My
No.
advice is never to drop.
No.
It's,
Unless,
that
of
other
course, you're
class was
failing, in
really
which case
good.
drop and try again. But,
I dropped him once, not.
yeah.
Oh, it happened?
We're past the date where you can do anything.
Yeah.
That's the other problem with 8-week courses, is the last day to do anything comes by really fast, right?
Maybe like a week drop.
Yeah. There's not enough time to figure out how we're doing in the course, really.
No.
So anyway, I'm thinking about it. What I may end up doing, I don't know. Yeah, I don't know. Because the problem is that the homework being the way it is, what I might just do is like, I don't know, drop your lowest one or something like that. But I'll have to think about it. But the problem is that I need to make a decision about it relatively soon, because I'm not going to go back and reopen like homework one or reopen all of them the last week of class or something like that. So I just need to figure out what I'm going to do. Like I said, the reason why I have interpretation whatsoever is because of the point of the homework being that it's supposed to enforce a out-of-class exposure to the material where you actually have to look this stuff up and apply yourself, so that you are refreshing this information in your head, as opposed to making easy mode where you can just take it over and over again until you get all the right answers. Which does improve your grade, which is half the point. Like, I'm not trying to punish you for doing bad on homework. I would like everyone to get, ostensibly, 100% of the points available on homework. But if I just do that and make it a completion grade, then it doesn't matter what you answer. You just answer something, you submit it, and now the homework is no longer serving its purpose either. So there has to be some sort of balance between those two extremes. Question?
May I pull the class real quick?
Sure.
Would anybody prefer if D2L sent us all its messages through one number.
What?
I get maybe 5 or 10 notifications a day, and they all come from FRM Help Desk, a different number, so they're never threaded, they're never put all together.
Text messages.
Yes.
Oh,
I didn't even know you could do that.
I did not.
Yeah, I'm getting text messages.
Okay, 'cause I didn't want to raise the issue with D2L and, well, I guess it only affects me, so I can't.
I do.
All right, I'll think about it. I will, question?
Can I, maybe offer a different solution?
Sure.
So,
I'm amenable to brainstorming solutions.
when I think about the homework, like I looked at one of the ones in the past, and I was like, well, what did I do wrong? And then I like redid it, and I was like, I'm still getting the same answer. And then I realized I rounded incorrectly, of all things. And so I just wonder if like going back in and redoing it, if it's gonna, you know what I mean? Like, if you don't know what part of it you did wrong, it's hard to like learn from it.
True.
So if
So you're saying multiple attempts would still require you to actually try because,
well,
or,
no, like it would still get you to try. I just don't know if it would help. Like I need to see like what part of it I messed up in order to learn from it.
right.
And so if you just said like, no, that's wrong, and then I go and do it again, I'm like, well, every time I do it, it's turning out to be this. So rather than like having people go back in and do homework again, would you, like when I was in anatomy, she offered extra credit every now and then, so, no, don't agree with that.
I'm okay with extra credit built in, like if we could do
Yeah.
in-class clicker type things or something like
Yeah.
that. I'm okay with that, but what I really don't like is extra credit assignments that that only get done by students who are particularly problematic with
Yeah.
respect to a specific grade. Because
That
like you
makes
got a
sense.
93, you're not going to do that.
Uh-huh.
So if it's something that that can incentivize everybody equally, then I'm okay with it. But an extra credit assignment like that does not serve that function. I understand what you're asking for.
Mhm.
I'll get to you in a second. Wherein like seeing that you rounded wrong, and if I had a larger bank of homeworks where I could be like, okay, here's that same type of question, now do it again, but don't make that mistake. But otherwise, if I just give you the answer so you can see what you did wrong, then you're just going to put in the right answer the next time you do it. So
Right, yeah,
so I can't do that.
I know, I don't think, yeah.
Right. So once again, there's this like, you're first. What's up?
Totally down for like the clicker thing, but also you could possibly work out the problems. So like when we go back to look at the ones we missed, it would have the answer there and show like the solution and like all that stuff. A lot of extra work for you though.
Yes. The other thing I could do is actually do for the homework at least do the short answer, because there's enough points. I think somebody in here, I don't want to point a finger, answered one of the questions and actually worked it out in the answer box. So of course they got everything wrong, because the answer box was for like 42 and not all of the equation, right? But if I'm gonna actually just go in and look at it, then I can see how you did it, and then I would see, oh, you just rounded wrong, and then I could give you partial credit for that answer.
I hesitate to mention this, but every problem in this book, every problem on the test is on answers. It's all over the internet.
Especially the homework questions back in the book type stuff. Well, I mean, I pick ones that aren't already answered in the book,
Right.
but
But even if you can't find that one, you can find almost identical problem with different numerical values, and people work the.
and you can also find half the questions in the back of the chapters the answers are actually available in the back of the chapters, which is why I picked the ones that aren't pre-answered for you. But once again, that exact same concept applies. They usually come in twos. One set of questions is pre-answered for you, and one set of questions is not. So if you want to prepare for the homework, you guys know where this stuff is coming from. It's going to come from the back of the chapter. So if you want to prepare for it, or while you're doing it, since you have all week, if you want to wait and figure out what it is first instead of doing the entire back of the chapter, you can just do the one similar to what I picked until you're confident that you can do it right, then do the one in the homework. That doesn't help people who did poorly on the first and second homeworks.
But you still gotta be careful with the answers. They are out there, but you gotta be careful because I have found a lot of those to be wrong.
That is
Because
true.
it's just people like us doing them and then posting it saying, here's all the answers. Well, they're not always 100% right.
Right.
Yeah, I use
Or-
the specific gravity of urine question on the test. Because the person worked out exactly the way I'd worked out, then I went to find the answer to confirm I did it right. It's like, oh, I wasn't sure. But now I'm confident, click.
But, and then the other problem is that different books use different constants. So if the specific gravity of something is listed as 1.06, but in another book it's 1.064,
Right.
right?
Yes,
And
that
so
is-
the math will be different, and so now, like, you, and at multiple choice, you could still be like, well, I got 13.9, then there's a 13.8, and nothing else close to 13.9, so it's probably that one.
I think on the quizzes, just being able to do it twice would be nice, just because we can go back and go, okay, we got this wrong, so let me refigure this, and I know that I can't get that same answer because that was wrong. So it will make you look it up. For me, I look up YouTube videos and stuff, just to show, not the answer, but show how it's worked,
Right.
because I know I did that wrong. So I think with the quizzes, that would help.
Like I said, I'm amenable to doing multiple attempts on the homeworks maybe, because like I said, that's like, I'm okay with everybody getting full points on the homework. That's half the reason why it's there. But I don't want to enable that, and by doing so, disable the other function of the homework, which is to force you to work on the subject. And granted, if you're a good student, you probably wouldn't abuse that, but at the same time, I also know that, like, it's the old difference about fences make good neighbors, which is actually a total lie. But the locks keep people honest type of thing. Like, if there is some sort of penalty for doing it wrong, then you're more likely to try, even if otherwise. Because once again, I understand everybody's busy, everyone has life, right? You don't have time to spend 16 hours a week studying for chemistry. But there's a medium in there somewhere, which will probably end up turn into me giving you guys like 2 tries on the homework or something like that. So, because I can't really think of a good middle ground. In subsequent semesters, do you guys have clickers here at Columbia College?
It's a clicker.
I don't even know.
It's like a little in-class thing.
We don't, but there's a program out there called Socrative that some of my teachers have
Are
used
using
in
like that
class.
for
Yes.
in-class quizzes?
Yes.
Right. So that's what I like to do for attendance bonus points, effectively, where if you come to class, you're here for quick little learning checks, and if you get it right, then you get credit, and then it's not a lot, but it's like
Yeah.
5% bump on your grade
It's
type
like
of
a
thing if you're
5-point
here every day
thing,
and you're
yeah.
taking part and trying.
You just have class at Olive Garden, and then they've got those little touch screens.
Very similar to that. And I know that there are phone apps that are like that too, but once again, it would be how do I integrate, how do I give you credit for doing it, right? As opposed to just handing out a sheet of paper and having everybody write down. Like before I had clickers back at my other university, I literally had people write down a few answers on a half sheet of paper and turn it in every day, and that was a pain in the butt. There's only 11 of you, so it wouldn't be that bad, but during a regular term when there's 30 people in this room, that would get a little prohibitive.
No, literally Socrative, if you look it up, there's a student and a teacher. And you actually can put it up there, the questions will be up there, and we can access it. You just have a code, and we have a phone app deal.
Right.
And it ties into yours. And I've had several teachers use this, it's the same
And then I would
idea.
manually enter it into the gradebook?
Yep,
That might work. I'll need to look into that.
I've had several teachers use that.
Assuming, of course, that everyone has a smartphone, which
Oh,
is
come
probably
on.
true 95% of people, but there'd be that one person, I don't have a smartphone, I can't get these points.
But if they don't, I've let people who haven't brought their phone, they've used mine to sign in and do it.
Or they could just hand me a sheet of paper.
Yeah,
One student where I have to manually check his that.
All
right, so- That's probably, the only reason why we're spending this much time on this subject right now is because chapter 8 is very short. So we do have chapter 9 posted, not that I posted it early enough for anybody to really have time to print it out. So we will play around with working with some working with some practice problems from chapter 7 and or 8. And then if we still run out of stuff and everybody is feeling like we just got this, then we could move on and maybe take a whack at chapter 9, depending upon how close to 8:55 we are by that point. So that's the plan for tonight, okay? So, let's talk about gases. There are a lot of different tests that you would use as a respiratory therapist. Being someone who has asthma myself, I have been subjected to many of them. So when we're dealing with respiratory issues, it's a subject matter that is close to home for me, but also very topical for this chapter, since respiration is the mechanism through which you acquire and exchange gases between your internal compartment, if you will, the blood compartment, and the rest of the world around you, right? So, let's talk about that for a little bit. Properties of gases. Oxygen gas, which remember, oxygen is one of those slightly odd guys that comes as a diatomic molecule, just like hydrogen and the halogens as a group. So, oxygen, and nitrogen for that matter. So oxygen is about 21% of the atmosphere. Vital to all life processes. It is, well, all. You can put air quotes around all if you want. Plants and animals, yeah, pretty much still true. It is not vital to all life processes, period, because there are organisms that are capable of surviving under anaerobic conditions, which is the same thing that you think of when you think about anaerobic exercise. It's living in the absence of oxygen. In fact, there are some organisms that are facultative anaerobic organisms, which means that if oxygen is around them, it will kill them. So not only can they survive in an anaerobic environment, but they would die in an aerobic environment. It's not actually that hard to find an anaerobic environment. Take a shovel, a standard size shovel, and pull out a chunk of dirt, and the earth that you just exposed was anaerobic before you exposed it. In fact, more than half of it is. It only takes about 3 to 4 inches of regular topsoil for the oxygen content to drop to 0. So the things that are in the soil in the first inch or two are using up the oxygen faster than it can diffuse down into the soil, and so anything beneath that is going to be anaerobic. Which does not mean that any cave you walk into will kill you, because that's a totally different mechanism for gas exchange. But still, oxygen for animals, which are facultatively are multicellular, as well as plants, which are also, by definition, multicellular, because that's one of the characteristics that we use to define what an animal or plant is, at least at some stage of its life, do require oxygen. The rest of the atmosphere, by and large, is nitrogen, which is perfectly inert. Once again, you can't do anything with nitrogen. We need nitrogen, you need nitrogen just as much as plants do, but the nitrogen that's in the air is N2, which is held together by an extremely strong triple bond. You can't do buckus with that. So I mentioned earlier that there, I think it was Oklahoma, that was thinking about reinstating effectively a gas chamber for their, instead of lethal injection, because their drugs were going to expire and it was getting really hard for them to find them. They were thinking about creating a nitrogen gas chamber where you would sit in the chamber and know that your death was coming, and then just kind of get tired, eventually pass out, and then a few minutes later be dead. Because nitrogen is perfectly inert. You can't do anything with it. And without oxygen, you would suffocate. Die. O3, otherwise known as ozone, is formed in the upper atmosphere when oxygen interacts with ultraviolet light. It is also formed in the engines of cars, because ozone is one of the primary contributors to smog, which is something that most of you probably at least know of, if not remember what it's like to be around and or breathe smog.
Grew up in Los Angeles.
Mhm.
So yeah, it's one of those things where nowadays, or at least until recently, we've been very concerned about having clean air. And so regulating the amount of ozone that we are producing in things like cars was something that we cared about. But back in the 70s and a few years before then, we weren't so much cared about it, which is one of the reasons why smog was so bad. It's one of the reasons why the Beijing Olympics, they effectively kicked cars out of the city for the 3 days previous to the Olympics to try and clear up some of the smog, since they were, hosting the world's largest worldwide sports event. They also did a few other things to try and get rid of the smog, with marginal degrees of success. There are other gases in the atmosphere: argon, carbon dioxide, water vapor. There's a lot of different gases in the air that we breathe, and obviously going to different areas is going to possibly change that composition to one degree or another. There are a lot of studies that show that the air inside a building is actually much less healthy than the air outside of a building, and that is because the way that we circulate our air, we tend to concentrate all the pollutants, pollen, mold spores, and otherwise in the air instead of replacing it with fresh air from outside, because out there's all that other bad stuff, like all the bad stuff we have in here, except usually less of it. on certain days when there's really big spikes of pollen, then yeah, there's probably more pollen out there than in here, but we don't exactly handle that very well. So learning goal for this, the kinetic and molecular theory of gases and how we measure them. So, a gas. What is a gas? It is a physical state that we use to describe matter. Matter comes in the form of solids, liquids, or gases, right? Now there are more than those 3 states of matter. That goes way outside of the box for this class. But in order to get to them, you have to do really weird things with pressure and temperature and volume to get odd states of solids or odd states of liquids or odd states of gases, right? So, we will not really get into that in here, but I do like to point it out that there are more than 3, but those 3 are the ones that you're going to deal with 99.9% of the time. So, solid as an S, liquid as an L or a Q if you're in an aqueous solution, and G for a gas. But what is a gas? Lots of small particles, i.e. atoms or molecules of that gas. CO2 is not an atomic gas, it is a polyatomic gas, right? So it's molecules. They're moving in straight lines, they don't curve around, they have essentially no attractive or repulsive forces towards each other because they are too spread out. They cannot be attracted towards nor repulse other things away from them. They tend to be very far apart. They have very small volumes compared to the volume of the container they occupy. That sounds a bit weird. So what do I mean by that? We mean that the density is very, very low. Does that clear it up at all? The amount of matter in a gas is very small for the amount of space that that matter occupies. If you were to go from a gas to a liquid, you would occupy, even with the same amount of matter, even with the same number of moles of that substance, it would occupy a much, much smaller volume as a liquid than it would as a gas. So the volume that it takes up is very large compared to the amount of matter that you find within that space. In other words, the density is very, very low. The kinetic energies of those atoms increase with increasing temperatures. So, gases move rapidly in straight lines. What this means is that the air that you are breathing into your mouth right now, into your lungs, and then breathing back out, all of the atoms and molecules that make up that gas are moving in straight lines up until the point where they collide with something else. It's like a really big game of pool with literally quadrillions upon quadrillions of balls bouncing around in 3-dimensional space. They move in a straight line until they hit something else that makes them change, and then both of those 2 things move in new directions based on the vector math of the velocities and angles of impact and blah, 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 things we don't care about. That concept of collision is going to be important here in a little bit. What are some properties that describe a gas? Well, all gases will need, in order to be a gas, we will have a certain pressure for that gas. Gases will all have certain measured volumes, even if we cannot determine it, like what's the volume of gas on Earth? Somebody could do that math. It wouldn't have very many degrees of significant figures, right? But somebody could probably do that math based on average, just height of what we consider atmosphere, surface area of the Earth, blah, 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 blah. Temperature. Gases have a temperature and an amount. The only thing that's really different between, because even solids and liquids are still going to have temperatures, solids and liquids are going to have amounts. Solids and liquids are also going to have volumes. So what's the only difference between a gas and solids and liquids? Gases have pressure. And theoretically, actually liquids do too. Even solids would sort of have a pressure if you found yourself under them. If you were underneath a car, would you feel pressure from that car? Yes. It wouldn't be gas pressure, but the weight of that car would most certainly push down upon you, right? Here we have the units that we can measure those in. Atmospheres, abbreviated ATM, millimeters of mercury, mmHg, which can be converted to inches of mercury if you're just really gung-ho about American system of measurements. Torr or pascals, volumes in liters or mils, we talked about that. Temperature in degrees Celsius or Kelvin, grams in G, mole is in N. N, little italic N is the number of moles of a gas. The volume of a gas is the amount of space that that gas occupies. Really only useful if we have already predefined that volume by putting that gas into a container. It could be a container as simple and easy as a balloon. It could be a container that's quite literally just a container that you open up to the air around you and then seal the lid, and now you have a specific volume of air inside that container at the same pressure as the rest of the volume of air, as the rest of the air around it. Here's the thing about volume. The volume of a gas tends to increase as the temperature increases if the pressure is allowed to remain constant. That's a lovely little sentence that we're going to come back to and give a very specific mathematical relationship to in a little bit. All right, temperature. The temperature of a gas is the average kinetic energy of the individual molecules within that gas measured on the Kelvin scale. This is very important. If you have your notes in front of you, find a way to highlight Kelvin temperature scale. Because the math that we're going to talk about subsequent to these pages are all going to assume that you're talking about temperature in Kelvin. So if any temperature is ever given to you that is not Kelvin, the first thing you need to do is convert it to Kelvin. Because if you try and do any of these problems using a Celsius temperature, you will get it wrong. Because Kelvin does not go negative. And it starts at what? What's 0 degrees Celsius on the Kelvin scale? 273. So you can understand if we're multiplying by 0 versus multiplying by 273, or dividing by either of those numbers, we can get with some very different answers, right? Up to and including infinity for dividing by 0. You can't do that. Why would the... Alright, so just two statements here, which I guess we're going to be able to explain in a little bit. When the temperature of a gas decreases, the molecules are going to have fewer collisions. Molecules, as the temperature goes down, the molecules are moving slower, right? So the number of times they're going to run into each other, or the boundaries of their container, is going to go down because all of them are moving slower. If the temperature goes up, the number of collisions is going to increase because all of them are moving faster. Therefore, the number of collisions per unit time will also go up. Make sense? Think of it in terms of, I don't know, preschoolers before sugar candy and preschoolers after sugar candy. How many collisions do you get? The more sugar you add, the more collisions you're going to see. Pressure. What is pressure with respect to gas? Pressure with respect to gas is effectively the same thing that it is with anything else. Because what is it about a weight that is put on you, like if you were to lay down and I was going to take a 20-pound weight and put it on your chest, you feel that pressure, right? What is that pressure? It is the force being exerted upon you by all of the molecules of that weight that are actively pushing down, and therefore, due to our understanding of physics, your body is also therefore attempting to push back, right? But that collision between you and that weight is the pressure of the weight of that object. Gas, it's hard to appreciate how much gas weighs, right? We're going to talk about the weight of gas here in a little bit, but when we're in it, it's hard to appreciate how much it weighs. But it is pushing on us right now, just like that 20-pound dumbbell would if I put it on your chest. You're just used to it. Now you could notice that difference in pressure if you went higher in the atmosphere to where the pressure decreased. You might notice that difference. If you went much, much deeper, or if we went into a room where the pressure increased, anybody ever gone into took a plane trip, right? You can, why do your ears pop? Take some gum with you or something? What? They pressurize the cabin, frequently in a less than comfortable and easy manner of doing so, because they just do it nice and quickly before everybody's ready for it, or otherwise. And that pressure is a difference. The air is pushing back against you, and you can feel the moment when the cabin is pressurized. That pressure comes from the impact of those particles hitting you. You do not feel the pressure of the air over there. You feel the pressure of the air that is in contact with your body. And all of that air will have a certain pressure based on ostensibly the volume that you're talking about, or if you're talking about atmospheric pressure, it is because of all of the other molecules of gas on top of you that are colliding with each other, forcing the ones lower and lower and lower to have greater and greater and greater pressure, because there's more and more and more collisions within that space. More and more molecules to collide more and more often, therefore increasing the pressure. This is why here we have a certain pressure. That's why you have to pressurize the cabin when we go up to 30,000 feet, because the air gets really thin up there. It's hard to breathe up there.
Just like if you climb Everest.
Yes, if you try and climb really tall mountains, at some point you will have to, if you have any degree of intelligence, augment your breathing with oxygen canisters or otherwise, because the air is so thin that the effort that it takes to continue climbing, you cannot get enough oxygen out of the air in order to fuel that exercise. A barometer is an instrument that we use to measure pressure. One of the original barometers, once again, played around with a very dangerous liquid, mercury. Mercury is the liquid, or the metal that is liquid at room temperature, right? But if you created a vacuum chamber and dipped it into a pool of liquid mercury, then at sea level, that mercury would rise up into that vacuum sealed tube up to about 760 millimeters. You guys can do this at home quite easily. If you just take a cup and get into the tub and put the cup on the surface of the liquid, and you just watch all the liquid just jump right up into the cup, right? No? That's not how that works? Of course not. It doesn't work that way. Because that cup already has gas in it. We need a vacuum here, right? But even if there was a vacuum, the water would not simply whoosh, fly up into that cup either, because there's this force that we all know about that's constantly pulling everything down, right? What's it called? Gravity. So, the act of this mercury filling this vacuum-sealed tube is literally fighting gravity. Where's the energy to do that coming from? It's coming from all of the collisions of the atmosphere on the surface of that liquid. Now, why does this have to be a vacuum? Because if this was full of air, then what would all of this liquid be doing as it rose up into that tube? It would be displacing the air in some manner, or increasing the pressure of the air up here, which would make this much harder to measure. We don't want to measure what the pressure of the air is in this tube. We want to measure what the pressure of the air out here is. So what this is telling you is that 760 millimeters, 76 centimeters, if you have a tube that has no air in it, just the pressure of the atmosphere around it would push that mercury up that tube to a height of 76 centimeters. That's kind of an impressive height. But that's at 1 atmosphere, which is this arbitrary thing that we call the amount of pressure that you find on Earth at sea level. 1 atmosphere. Which is why we have this nifty little conversion here. 760 millimeters of mercury equals 1 atmosphere, which equals 760 torr. The fact that the units are the same here, which means that in any example where it's asking you to convert between millimeters of mercury and torr, all you have to do is just change the label, because they are equivalent. Torr is a unit of pressure that we use to give credit to the guy who came up with the barometer, a way to measure pressure. Pressure at sea level, 760 millimeters of mercury, or 1 atmosphere. Pressure at this arbitrary mountain height, evidently 0.7 atmospheres. As we go up, the atmospheric pressure goes down. Why? Because there's less air above you pushing on you. This same concept of pressure also applies to water, which we're going to talk about when we start talking about liquids in chapter 9. Water pressure, as you go down underwater in the ocean, you're going to watch those like submarine shows where there's like, we're reaching maximum depth, and the alarms sound, and sometimes like little leaks will pop and water will start spraying in or something. What's going on there? The deeper you go, the greater the pressure of water. And a high enough amount of pressure will crunch a submarine just like you crunching a tin can. Here are some units for measuring temperature. Atmospheres. Now, here are these top 3 up here. We have this little abbreviation that tells you exact, which means what? If you're doing calculations, it will or will not impact your significant figures. If it is an exact value, it does not impact significant figures. So 1 atmosphere, that would kind of suck if you're like trying to do math of one atmosphere. Like I have 1 sig fig. So atmosphere is an exact amount because we have declared it to be so. So it does not affect significant figures. Neither would, or I should say the conversion between 1 atmosphere and 760 millimeters of mercury. But if you want to convert 1 atmosphere to 29.9 inches of mercury, that's, now we have only 3 significant figures. Because that is not an exact conversion. Pascal is a very small unit of pressure, 101,325 pascals at 1 atmosphere. So frequently, you'll see pascals written as kilopascals or kpascal, kPa, just because that makes it a slightly more manageable number. Atmospheric pressure changes with variation in the weather and altitude. On a hot day, the atmospheric pressure increases. Why? What is temperature? Measure the kinetic energy of the molecules in the gas, right? What is pressure? The amount of force exerted by the collision of molecules of gas on you. So, if we have more energy and more collisions, what's that going to mean? More pressure.
But
well, yes,
it's a lower volume.
Well, lower volume if it actually had room to grow, but the rest of the atmosphere is huge and pushing down on it. Doesn't have, there's a bit of an expansion.
You're just saying it's at surface level.
Yes, well, if you're staying at sea level, there's the rest of that pressure above you that's keeping it there, keeping all of that air there.
It's the density altitude in winter. You
What's
want
that?
to get it? Oh, pilots think about the density altitude.
Yeah.
How thick the air is at higher elevations, which make for a nice smooth flight.
And changes, and well, how many guys have you ever experienced, what's the word, dang, when you're flying, turbulence. What is turbulence?
Different layers of air temperature.
Temperature which causes differences in what?
Density.
Density, which is equivalent to pressure. So, yeah, regional differences in pressure.
Yeah, so low humidity cool temperature days, private pilots are allowed to the field.
All right, let's talk about a little bit of math. Boyle's law. Spelled B-O-Y-L-E, not B-O-I. Boyle's law. An inverse relationship between the pressure and volume of a gas. So by inverse relationship, what we mean is as one goes up, the other goes down. If it's a linear relationship, then as one goes up, the other one goes up, right? An inverse relationship says when one goes up, the other one goes down. So, we have an inverse relationship between the pressure of a gas and the volume of a gas. That is Boyle's law. Oxygen therapy increases the oxygen available to the tissues of the body by adding more oxygen to the atmosphere as we breathe it, which increases the partial pressure of oxygen, which increases your body's ability to absorb that oxygen and carry it. Now here's the thing about Boyle's law. It assumes that the temperature and the amount of gas in question does not change. So, the pressure and volume of a gas are inversely related as long as the temperature and amount of gas does not change. Here's a piston and a cylindrical container. The volume is 4 liters at the beginning. The pressure is 1 atmosphere at the beginning. But if we were to take that piston and push it down, applying force to this container, that would increase the pressure, but also decrease the volume. So, that means that the product of pressure and volume between two different states are equal to each other. So Boyle's law can be mathematically stated as this. P1V1 is equal to P2V2. What's the one substrates here? We could also put PIVI is equal to PFVF. What would that be? Pressure and volume of your initial condition and pressure and volume of your final condition, right? The 1 and the 2 is initial, or the first condition and second condition. So, what that means is that you should be able to, if given 3 out of those 4 things, you should be able to solve for the 4th, right? Quite easily. This is quite simple algebra. If the thing you don't know, whatever the thing you don't know, divide by the thing next to it, and that's how you solve for it, right? If you don't know the initial volume, but you do know the final volume, the final pressure, and the initial pressure, just divide P2V2 by P1, and that gives you your initial volume, right? Like this is very easy algebra. P1V1 equals P2V2. Solve for the thing you don't know. With the caveat that you want to make sure that your pressures have the same units and your volumes have the same units, right? Because if P1 is in atmospheres and P2 is in pascals, that math is not going to work. So you need to convert it to something. Now this would work as both atmosphere or pascal. As long as both your pressures are in the same units, as long as both your volumes are in the same units, then this works. It doesn't matter what the volume unit or the pressure unit is, as long as they are the same between the left and the right side of the equation. Boyle's law states that the pressure and volume of a gas is a constant. Now, unfortunately, we are not going to talk about what that constant is much. I'm going to mention it later, even though the book never does, and it's going to have another letter, so I'll get to it at the end. But that means the pressure and volume of any gas, assuming that the temperature and amount is constant, remains the same, is equal to a constant, which means that it does not matter what you're dealing with, any gas at any pressure and any volume is equal to that constant, which is why we can then put this other thing here. So let me draw that out for you since we had trouble with that the other day. So our P initial, V initial is equal to a constant, which I'm going to call R. Told you I wasn't going to tell you that until later, but I'm writing it on the board, so I'm going to write it the correct way now. It's equal to a constant called R. Well, that, therefore, since that is a constant, any pressure times the appropriate volume is going to be equal to that, then that means that it will also be equal to our final pressure and final volume, right? Because any pressure and volume, if we're following the natural order of things, if you're not trying to force it somewhere else, right? Just that piston example. Any pressure and volume at any two different conditions are going to be equal to that same constant, which means we can make them equal to each other by just getting rid of this middle guy. Make sense? We're going to come back to that middle guy later. Once again, that's one of those slightly deeper than the book wants to take us type of concepts. So, 8 atmospheres and 2 liters is 16 atmospheres. 4 atmospheres and 4 liters, 16 atmospheres. 2 atmospheres and 8 liters, 16 atmospheres. I should point out that it looks like this is just arbitrary. These are not arbitrary numbers. If the temperature and amount of a gas is the same between two different states, then the pressure and volumes of that gas at those two different points will be equivalent. Period. End of story. It looks like we're just doing some nifty little math by pulling numbers out of our you-know-whats. But for any given gas, it will always equal that constant. Pressure, volume of your initial state is equal to the pressure times volume of your final state, second state. Assuming, of course, that temperature and the amount of gas is a constant. All right, so how does Boyle's law actually impact biology? True or false? When you are breathing, you are sucking air into your lungs. When you breathe in, you're sucking air into your lungs. Did you see that's true or false?
False.
Why would you say false?
You're actually letting the atmospheric pressure fill your lungs as your diaphragm gets everything out of the way and your muscles expand your rib cage to accommodate it.
So your diaphragm changes and your rib cage might also change, which is going to do what to the volume of your chest cavity? Increase it. Which is going to do what to the pressure of the air in your chest cavity? I.e. the air occupying your lungs. If the volume increases, the pressure must go down, right? Which means now there is greater air pressure outside of your body than there is inside of your body, so what's the outside air going to do? Flood into your lungs. So how do we breathe out?
Force it.
Muscular contractions of both the diaphragm or relaxation of the diaphragm, muscular contraction of your rib muscles to decrease the volume of your chest cavity, which is going to do what to the pressure? Increase it. And if it increases it beyond the pressure of the air outside, then what's going to happen to the air in your body? It will rush out of your lungs. So here's the thing. Remember how we talked about muscles never push, they always pull, right? A vacuum, we like to think of vacuums as sucking, right? Like when you're using your vacuum cleaner, hold your hand up to the end of that vacuum and what's it going to do? It's going to get sucked to it. It's going to get sucked. Like vacuums suck. That's what they do. But vacuums never suck. Vacuums create a differential of pressure and the rest of the atmosphere around it pushes. More to the point, if you took a vacuum cleaner into space, would it do anything? No. Because the whole reason a vacuum cleaner works is because it creates a low pressure inside the machine so that air will rush into it and hopefully take a bunch of debris and other crap that you want it to pick up with it. The true-false question I asked you about your lungs was a trick question. You create a vacuum in your chest when you breathe in. But air you're not sucking air into your lungs. If there was no air out there, there would be no air to suck in. It's getting pushed into your lungs. But we could call that sucking, right? Because when you have an atmosphere, you can create a vacuum that feels like sucking. Just like we can call something cold, even though that's an entirely subjective description as well. Regular frozen water feels pretty hot to dry ice, right? Both of them feel cold to you.
Ah, dry ice burn.
Yes. During an exhalation, your lung volume decreases, which increases the pressure. And when that pressure gets higher than the atmosphere around you, the air will leave. All right, let's do a calculation with Boyle's law. This is similar to what we have in our practice problems for this chapter, of which there are quite a few. We're going to work through one of them. Freon 12. Calcium, or carbon dichloride difluoride, was used in a refrigeration system. We still use freons, but we should be very careful about releasing them. So, what's the new volume of an 8-liter sample that was initially at 550 millimeters of mercury after its pressure is changed to 2,200 millimeters of mercury? Assuming, of course, that temperature remains constant and the amount of gas we're dealing with remains constant. Could you do that? So we have our initial volume, right? Well, no, sorry, that's the new. What is the new volume of an 8-liter sample? So initial volume, 8.0. Initial pressure, 550 millimeters of mercury, right? We have our final pressure, 2,200 millimeters of mercury. So what are we solving for? What's the new volume? V2. So, here's Boyle's law. P1 V1 is equal to P2 V2. Tell me what you think is going to happen. So we have 8 liters. It's at 550 pressure. But our pressure is increasing. So according to our understanding of Boyle's law, if the pressure is increasing, what is happening to the volume? It is decreasing. So that means that our volume, our V2, should be larger or smaller than 8? Smaller. As the pressure goes up, 550 to 2200, the volume should go down. 8 liters to something less than 8 liters, right?
2 liters.
Do the math. 2.0. Notice how this time they actually put the correct significant figures for our initial volume up here. And that one little oops on one of those examples previously. All right, so that's Boyle's law. Now, any questions about Boyle's law? We'll understand how we do that. If I give you initial temperature, and any 3 out of initial temperature and pressure and volume, or final pressure and volume, right? Then use Boyle's law, solve for it. You can put a pin in that if you want for a moment, because we're going to talk about 3 different laws, and all of them can be summarized mathematically exactly the same way, and that makes it much easier to remember all this crap. So, Boyle's law is for pressure and volume. Let's talk about Charles' law. If we increase the temperature of a gas, the motion of that gas will therefore increase. And so, if the amount and pressure of the gas is a constant, the volume of the container must increase. So if we increase the temperature of a gas so that it collides with things more often, if we're going to keep the pressure the same, the volume of that container must get larger. So here's Charles' law represented mathematically. V1 over T1 is equal to V2 over T2. How could we state this in English in a slightly more layman's way? Before, Boyle's law said as the pressure and volume have an inverse relationship, right? So when one goes up, the other one has to go down. If one goes down, the other one has to go up, right? What are we talking about here? Temperature and volume. Charles' law is temperature and volume. So as one goes up, the other one must go up. As temperature increases, volume must increase, assuming that pressure and the amount of the gas is the same. So Boyle's law is pressure and volume. Charles' law is temperature and volume. What does that look like? Well, if you put an amount of gas inside a container with a known volume and a piston on top just to seal the container, if you increase the temperature by adding energy, so here our T1 is 200 Kelvin, our volume is 1 liter. If we double that temperature, what must it also do? Double the volume. In this case, when we're doubling the volume, it's just raising that piston up a little bit higher. Now, a piston complex like this is not a perfect system because gravity also wants to pull that piston down. But, you know, in the absence of gravity, this metaphor works, right? For two conditions, we can write V1 is equal to, V1 over T1 is equal to V2 over T2. Remember that constant thing? Charles' law, the relationship between volume and temperature is equal to a constant. Therefore, we can put our initials as equal to our secondaries. So we can rearrange this to solve for whatever we want, right? If you get 3 out of 4 of volumes and temperatures, then you can use this to solve for it, right? Easy peasy. Basic algebra, right? So let's try. A balloon has a volume of 785 mils at 21 degrees C. If the temperature drops to 0 degrees C, what's the new volume? Assuming, of course, that we have constant pressure and the same amount of gas. So, conceptually, you can already tell me what direction the volume should be going here, right? We start at 785 mils, we're going from 21 to 0. What's happening to our temperature? It is going up or down?
Down.
Down. Therefore, understanding the linear relationship between these two variables, what direction must our volume also go? Down. When temperature goes down, volume goes down. When temperature goes up, volume goes up. So we know that the answer must be less than 785 mil. But in order to do that calculation, what must we do first? Correct, convert it to Kelvin. Because you cannot divide by 0. Right? In this case, T2 would be 0. If we left it in Celsius, our second temperature is 0. You cannot divide by 0. Plus the math would be totally different. So we convert to Kelvin. So here we have 273 as our final and 294 as our initial. Right? I just added 273 to both of those. We then solve for that. So here's our Kelvin temperatures. Solve for V2. How would we do that? Well, V1 over T1 is equal to V2 over T2. I would just take T2 and move it over, multiply by T2, right? Cross multiply it over there to T over there. So T2 times V1 over T1 is equal to V2. Everybody follows that, like, first 2 weeks of algebra step, right? Okay, good. And when we do that, we get 729 mil. So it didn't go down by a lot, but it did go down, right? Now why did they write this out this way? Why did they write 785 mil times 273 Kelvin over 294 Kelvin? So that we can cross out both of our Kelvins to make sure that we're doing this right. If you write this out, then the answer should have the units that you want. If it doesn't, then you did some math wrong, right? All right, So that's Charles' law. What about Guy-Lussac's law? It's a good thing you guys can just look this stuff up, right? That I haven't remembered which law was named after which dude. Guy-Lussac's law states that when the Kelvin temperature of a gas is doubled, when the volume and amount of gas does not change, the pressure also doubles. All right, put that in layman's terms for me. When the temperature goes up, the pressure must also go up, assuming the volume stays the same, right? Because we just learned that as the temperature goes up, what happens to the volume? The volume has to go up, right? If the pressure is going to stay the same. Well, if the pressure is not staying the same, or if the volume is staying the same, if that can't change, then the pressure has to. Once again, temperature at 200 Kelvin, pressure of 1 atmosphere. If we double the temperature without changing the volume, if the volume is constant, then the volume cannot change, so therefore the pressure must change. So if we double the temperature, what happens to the pressure? We double the pressure. It is a linear relationship. Therefore, we can write this out like this. P1 over T1 is equal to P2 over T2. So once again, if I gave you 3 out of 4 of those, you could solve for the unknown, right? Assuming, of course, that the volume and the amount of gas are held constant. All right, let's try that once. A gas has a pressure of 2 atmospheres at 18 degrees Celsius. What is the new pressure when the temperature rises to 62 degrees Celsius, but the volume and amount of gas stays the same? You already know conceptually which direction that pressure should go, right? The temperature is going from 18 to 62. It's rising. So what's going to happen to the pressure? It will also rise. It will get bigger, right? By how much? Well, for that we would need to know math. What's the first thing we got to do? Convert Celsius to Kelvin. So that's what this is for. We need our secondary pressure, so we take this equation over here. We solve for P2 by just moving T2 up next to P1. So T2 over T1 times your initial pressure is equal to your new pressure, which is exactly what they did there. P1 is equal times T2 over T1 is equal to your new pressure. Just a bit of algebra, right? Easy peasy. Plug in your numbers. 2 atmospheres to start with. 335 Kelvin over 291 Kelvin. The Kelvins cancel out. That leaves us with 2.3 atmosphere. What direction did the pressure go? Up. Temperature increases. Pressure increases. All right, so we have 3 different gas laws. But all of these gas laws can actually be combined together. The combined gas law. It gives us a relationship between all 3 of the variables that we have so far been discussing. Pressure, temperature, volume, and actually there's a 4th variable that keeps hiding from us that has been mentioned once or twice, the amount of the gas in question, right? So, here's Boyle's law, where we have the relationship between pressure and volume where temperature is constant. Here's Charles' law, where we have a relationship between volume and temperature where pressure is constant. Here's Guy-Lussac's law, where we have a relationship between pressure and temperature where volume is constant. Even if you weren't good at algebra, I would hope that with those 3 things right in front of you, it should be pretty easy to see all 3 of those variables are there in all 3 of those equations, right? It's just that if it's the same on the left and the right, we don't write it down. Right? So that means that the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. You can use this equation right here for any and all of the previous examples. Even if you did plug in the thing that stayed the same, it would give you the exact same answer because the thing that stayed the same would be the same on both sides. So let's go back to this example right here. So, right here, here we go. So all I did was add that V1. P1 V1 over T1 is equal to P2 V2 over T2. You see, this is why I don't like smartboards. You touch it, and it thinks you're writing on it.
Erases better.
It does erase much better, though, you're right. So, P1 V1 over T1 P2 V2 over T2, right? Multiply times T2 on both sides, and that gives us a P2 V2 right here and a P1 V1 right there, right? But if V2 is equal to V1, which is what we mean by constant volume, right? Then does it matter? We have the same thing. So what that means is, if P1 is equal to V1, or P2 is equal to V2, then we can change that V2 to V1, right? Same thing. So V1's on both sides of the equation. What can we do to this? Divide both sides by V1. It doesn't matter what that volume is. It could be 1, or it could be 4,386,7,000. Right? If we divide by it, then what does V1 over V1 equal? 1, which means it has no impact on the math, right? Not exactly to scale for where we're erasing things. All right. So, that's our combined gas law. You can use this equation to solve any of the previous ones. Just by going, all right, what's not changing? And whatever's not changing, drop it. Right? If volume's not changing, then we drop V, and what do we have? A relationship between pressure and temperature. That's Guy-Lusac's law, right? If pressure's not changing, then we drop it. We've got V over T. That's Charles' law, right? There's one other thing that never changes in any of these things right here. That little n. What did that little n mean?
Number of particles.
Number of moles. Yes, which is a way to measure number of particles. The amount of the gas. In every example that we've discussed so far, the amount of gas has not changed. But does this mean that you could conceivably do math where the amount of gas does change? Yes. I doubt that you will, since the book has gone out of its way to avoid ever mentioning where n goes in this equation. A gas has a volume of 675 mils at 35 degrees C at 646 millimeters of mercury. What is the final volume of that same gas if we cooled it down to negative 95 degrees C and changed the pressure to 102 millimeters of mercury? Could you do that? What's the unknown? What is the volume in millimeters? So what's V2, right? We have V1. It's asking for V2. Do we have everything else? Yep. So we're solving for V2. So what would we do? Move T2 over here to the top, divide by P2, so we'd be down here on the bottom, right? Just do the algebra, get the answer. Multiply by P2 over V2 would be another way to put that. Or excuse me, multiply by T2 over P2. That way we cancel out on the right side and we add them over here on the left and you solve for V2. Basic algebra, right? So if we do that, V1 is equal to, now they're showing here P1 over P2. Here's P1. We're dividing by P2, right, to get it off the right side. So we put it over here, so P1 over P2. Now T2 is on the denominator on the right side, so we're going to multiply it over here, right? So T2 over T1. They're skipping some steps in here in the algebra. Right? Which means you need to do it to both sides. Make sense? So now, this T2 and this T2 cancel out. This P2 and that P2 cancel out. And so what are we left with? T2 over T1, which is this guy right here, right? And P1 over P2 which is this guy right here, right? Just algebra. I can see how this could get addictive, but also very wasteful of time. Erasing things on a smartboard. So if we do that, we plug in our volumes, we plug in our pressures, we plug in our temperatures, and we get 314 moles. Now remember before we asked the question, we could say like, well, if the pressure is going up, the volume has to go up, or if the pressure is going up, the temperature should, we could talk about the inverse relationship, the linear relationship, right? As the temperature goes up, the volume has to go up if the pressure is the same, right? Could we do that same thing here? Our volume, we're not sure about volume, but our temperature is going down, but our pressure is going up. So, is our new volume going to be lower or higher? One contributes a little bit, and so we can't make those obvious comparisons. But we can still do the math, right? And what ends up happening, 314 mils, we started with 675. So we have pressure going up, we have temperature going down. And we get a much smaller volume. Volumes and moles. Is this fuzzier than this here? No? Okay. STP. STP stands for standard, temperature, and pressure. We're going to define that when we get to the next section, which is why I wonder why they're using it here. STP is standard temperature and pressure. The molar volume of a gas at standard temperature and pressure is about the same volume as 3 basketballs. 22.4 liters. So I want you to appreciate something. At standard temperature and pressure, what would the volume of oxygen be? Pure oxygen. What if we make a difference? Chlorine at room temperature is a gas, right? We talked about that before. So, well, chlorine can actually be either at room temperature. But if we have chlorine gas at room temperature, then we have more or less volume than oxygen. If we have a mole of both, what's the volume going to be? Because the oxygen has a molar weight, right, of 16, based on significant figures. Chlorine has a molar weight of 35.45, if I can see correctly over there, right? But here's a question for you. Does this slide in here say anything about anything with respect to what atom or what gas we're talking about? What about CO2? What about nitrogen? What about hydrogen? What about helium? What about neon? It doesn't freaking matter. The answer to anything is, what's the volume of 1 mole of gas at STP? That. Now how much does that mole of gas weigh? That is different. But what's the volume of a mole of gas at standard temperature and pressure? That is 22.4. Why is it so important that we say at standard pressure, standard temperature and pressure? Because remember the ideal gas equation that we were talking about a moment ago? It had 3 variables, right? Pressure, temperature, and volume. So we're asking about what's the volume of a gas. Well, the answer to that question is very dependent on those other 2 variables, right? Temperature and pressure. If you don't know the temperature and pressure, you can't answer that third one, can you? Unless, of course, we say at standard temperature and pressure, in which case the math has already been done, it's 22.4 liters. That is Avogadro's law. That is the volume of 1 mole of any gas at STP. Which means that we have this relationship. V1 over N1 is equal to V2 over N2, assuming that temperature and pressure are constant. That's what STP means, right? Standard temperature and pressure, which means that temperature and pressure on both sides of the equation are the same, which means that we now have a mathematical relationship between V1 and V2 and N1 and N2. Does that mean we could add N to that equation that we just talked about with the other 3 guys? Where would the N go? On the bottom. So it'd be P1, V1 over T1, N, right? The idea here is, once again, there is a linear relationship between the amount of gas you're talking about in moles and the volume of that gas. As the amount of gas goes up, the volume of gas must also go up, right? If we have 7.75 moles of helium gas, and it occupies a volume of 1.5 liters, what volume in liters will 1.2 moles of helium occupy at the same temperature and pressure? Can you do that? We have our initial amount, N, right? We have our initial volume, V. We have our final amount, right? So what do we solve for? V2, right? This could be multiple choice. Let's try it. So what do we need to solve for? V2. So that means we need to multiply by N2 here, right? And therefore multiply by N2 over here as well. Does that work? Because we did it to both sides. Which means these go away. So that means we can erase this. So if we wanted to keep this in the same format that the book has been using, we would write that as N2. Hey,
The eraser. You
Oh.
put the eraser back.
got to sense the eraser.
You don't.
N2 over N1 times the initial volume is equal to the new volume, right? All I did was just change where the fractions were a little bit, but kept everything the same. So our N2 is 1.2 over 0.75. Our initial volume was 1.5 liters. If we actually did that math, what would we get? .4. Initial volume over times 1.2 over 0.75. Once again, the moles cancel out, so our answer is in liters, and we wanted an answer in volume, so that tells us we did it right. Is that I didn't follow look on your face, or is that something else? Okay.
Can you go back to the last slide? Or what you did? Okay, I see.
Good? Okay. I do like that it remembers what you did. All right. So that's Avogadro's law. That is assuming standard temperature and pressure. Did we define what that was? Did we need it for the last question? Could it have been any temperature and pressure? As long as the temperature and pressure stayed the same? Yep, it could have. But we didn't say at weird temperature and weird pressure, we said at standard temperature and pressure. So it would be useful to know what that is, right? Which is what this slide is for. What is standard temperature? 0 degrees, right at 0 degrees Celsius. So cold, from our perspective, right? 273 Kelvin. And what is standard pressure? That one should be easy. 1 atmosphere, right? 760 millimeters of mercury, or 1 atmosphere. That's standard temperature and pressure. Because you now know this, that means that it is possible that a question could ask, what would the new something or other be if we changed from standard pressure to some new pressure? And that would mean that you would have to know that standard pressure was 1 atmosphere, right? Almost at 7. We're also almost done with this. Let's go ahead and take a 10-minute break. We'll finish this up, and then we'll balance some equations from chapter 7 and maybe do some math from chapter 8. Question?
Are you posting new homework?
Yes, tonight. It'll be, well, tomorrow 8 a.m. Possibly with the 2 attempt thing enabled.
Will that be enabled on our old ones?
Nope!
Oh,
Don't think so. Probably not.
this one that was due today.
I wouldn't mind it because I completely forgot.
You didn't do it?
I did it, but they shouldn't have done it right for the test.
Well, see,
And then
here's the
my
thing.
kids were running around going, Mom, Mom,
Oh,
Mom.
yeah, that's true. Here's the thing, though. Even just doing it, even if you do really bad, it means that you get 1 homework for free.
She even reminded me, I had no idea there was a homework posted.
I reminded you.
See, I
Yeah,
thought the
she
homework was
reminded
on
me.
Thursday, or it
And I
started
went
on
home
Thursday.
and I
It
passed
starts
out.
every Thursday.
I had so much to do.
And we'll
The
do-
test does, right? The
But the
homework
homework
starts
did
on
too.
Tuesday.
The,
Did
well,
it?
yeah. The homework opened at the exact same time the test did.
Mhm. And I took it right after the test.
That's actually probably why I missed it, is because of the,
Okay.
Yeah, because it opened, maybe you didn't see 2 announcements, or maybe it only gave you 1 announcement for both.
well, that's
Yeah.
stupid FRM. I mean, I've got 50 different people messaging me, except it's all the same person.
Yeah, but for point of fact, from here on out, I mean, I can take a look and see how many people screwed that up and maybe be nice. But point of fact,
Oh, I'm not looking for.
there is a homework that opens every Friday morning, and it will be due Thursday before class the next week.
I'm not
As
gonna let
stated
that
in the
be
syllabus from the beginning of the semester, as of week 2, every week there will be a homework. Just makes it easier for me to just say there is, and that instead of like, I haven't made one yet or something.
I'm surprised I didn't miss it, because I have a teacher who every time we take a test, we don't have a quiz that week.
Oh.
So if I hadn't looked at it, I would have missed it.
I can totally see why, like, oh no, we have a test this week instead of homework. Like, nope, every week.
Yeah.
I know in the syllabus it said that the exams were worth 100 points. So
Each.
Are you gonna go back in and change that on the grades?
Yeah, I'm gonna calculate the grades.
It's
So
Okay.
it'll be a manual calculation.
Okay, yeah,
But
cause I
because
saw
it'll be,
that.
which is why because it needs to be based off of the percentage point, and I'll figure out how to make the grade book do that eventually.
Okay,
But right now it doesn't matter, because what's gonna happen for your finals is I'm gonna export them all, I'll calculate your grades, and then import them, and it'll be what I say it is. Done. But it'll be based on
but
that
like
math.
for the most recent exam, that was 48
Look at your
questions.
percentage.
So I would just say that the percentage is how many points?
Yep. Yes. It is a direct linear comparison. So if you got an 87.39, then you have 87.39 points.
But the homework's different.
The homework will all add up, and then the total amount will be 100%. Which is why there's 7 12-point assignments, and you get to make one sort of for free. Like, what? So you actually get like 16 points for free if you do all 7.
Okay, I'm gonna put you in
For
form.
some reason, I thought homework number 2 was coming out today.
Probably because the test,
Lock your fingers.
because of the leapfrog test. But yeah, every week.
Give me a little bit of your weight.
Because you said we already had it, and I'm like, oh.
Yeah.
I'm guessing something to help with that.
That's way better.
Question for you.
Sure.
Can't really see the writing with the lights off, and it creates a huge glare on the video. Not that the video is important, but I'm wondering, do we need the lights off? Does anybody?
Well, we can turn the lights on, but then you're gonna have a huge glare reading the slides the whole time.
Will we?
Right.
Yes.
Okay, then never mind.
Yeah, so that's why I turned them off. But yeah, it probably does make it very difficult to see what I wrote on the board.
Yeah.
I guess, do you want to write on the board?
I could, yeah, just write it in the white space. Yeah, do that. All right, I'll be right back.
The C2.
Why is it so cold in here?
It's funny. It was too hot. I turned it down. I'll turn it back up.
It was like the
But I've never
perfect
seen these videos.
amount of heat.
That's my fault. That was my fault.
I'm just.
We always know to all bring jackets or wear long sleeves.
Socks.
Yeah.
This kid's got a great idea.
Yeah.
Snacks, spring snacks.
Yeah, my back's killing me. That's why I got up.
I usually do once a month, and I just never know.
So where is it hurting?
My back is
Oh, well, I can do lower than your cervical vertebrae as well. If you want to go stand up against the wall. No, it's just until I got a silicone ring, it would hurt me. Just back against the wall.
Oh, that's amazing.
I love it when you do that for people, but people can't do it for me. Well, I try actually disconnecting one of my ribs. That was fun. I was after my wife when I was courting her, so obviously I was after her. But I was watching her be a question mark. I mean, she's an engineering student, so you know. And we were all coming out of Whitmore Recital Hall one more night. and it's painful walking behind her. And I offer again. Yeah, I offer again, and she turns to me again. And then she said, okay, what do I have to do? I said, just give me a hug. And I started about at the top of the lumbar, up. It was so funny. She walked away from me, she says, yeah, that didn't help.
Oh, yeah, it just stretches up, yeah. Yeah. Because you get used to just being like that.
Yeah.
Looks like you're drinking a small keg of beer.
I know! It's a Bubba jug.
I almost started laughing.
It's even got a can opener right there, just in case you need to refill it.
Wow.
It literally looks like you're
Or a
drinking
bottle
small
opener, excuse me.
kegs of beer.
I believe the last meeting, we were discussing the healthy water.
Yes, exactly. Today was the arbitrary day of self-medicating for caffeine so as not to get a caffeine headache. And changing a handful of other things too. So I still may have sodas in here for a few weeks. It just depends on whether or not I start getting a headache, because I am fully addicted to caffeine. It's like I'm a smoker. I'm not a smoker, but that's my metaphor. Like, I've tried to quit multiple times, so I know what caffeine withdrawal is like. So if I start getting that headache right about there,
Yeah.
but I don't have caffeine pills at work. So pop caffeine pill in the morning. Eventually that'll be where all I need, and then I'll stop doing that like every other day, and then I'll just taper down to where I don't need it at all.
Caffeine pills are hellacious. They're a massive dose.
It's about the same as a cup and a half of coffee. It's
Just
not
go to-
massive, but yeah, it's a lot of it in a relatively short period of time because they're not like time delayed.
Go to Think Geek and you can order caffeinated soap.
Well, I'm sure you can order caffeinated everything.
Huh?
Does it actually work?
The absorption's not nearly what it is, it's consumption, but yeah.
Your skin absorbs.
Well, sort of. Certain chemicals can be absorbed
Right.
in your skin. The whole point of your skin is that it is a barrier. It's not supposed to absorb. So most things will not be absorbed through your skin, but certain things, especially lipid-soluble things, can still get through.
And acid.
That's not really absorption.
Yeah.
Oh, unless of course,
You're soaking in it.
right, yes. That depends on which type of it, like if you're referring to the drug, then that's different, but just exposure to acid on your skin is not absorption, that's something else.
If you could invent caffeine vaping, you have $1 million.
See, the whole I'm not trying, I'm medicating to get rid of it, not just so that I have a different source of it. That's not the point. I'm just trying to avoid migraines while I...
Isn't there a Gwyneth Paltrow character that was smoking to get off of the patches?
I don't know.
Well, like if you're smoking.
That sounds like it's something about Mary reference or something.
Wouldn't that hurt your body
Is that?
if you were smoking caffeine?
Wouldn't it what?
Would it hurt your body? Because you're like inhaling it in your lungs.
Well, the whole idea behind vaping is like cigarettes. The thing that's most dangerous about cigarettes is actually not the nicotine, it's the other chemicals in the smoke from the burning. Right. Well, it doesn't matter what you're inhaling. It's the whole idea like acid, the type, the drug, comes in two major forms. One that you put on your tongue, and the other one you just drop in your eye. Because everything about drugs, be it an illegal one or a legal one like caffeine or nicotine, everything is about how you get it into your system. And the fastest way to get it into your system, i.e. into your blood, is through the massive surface area and absorption that you have in your lungs. Other than just minimizing it, which is, none of this is
Drop
good.
acid in your eye.
Yeah.
They
That's
used
why they
to
call
keep
it dropping acid.
Yeah, they used to keep it in like eye
Eyedroppers.
drops.
Yeah, like
In the 60s
Visine,
and 70s.
yeah.
I
That
was
was
getting
popular.
to put in your tongue, but who's stupid enough to put it in their eye?
Oh,
Well, and that's one of the
It
reasons.
goes straight to your.
Yeah, well, this is, the whole point is, like your question of does caffeine soap work? Well, not very well, because the skin is not meant to absorb. The thing is, your eyes are alive. Those are live cells. The reason your skin is a barrier is because there's layers upon layer of dead cells that protect you from the outside from getting inside. Well, there's certain areas of your body where to do its job, it has to be alive. Your lungs, their job is to exchange molecules between the air and your bloodstream. Your eyes, the outer surface of your eye is not vascularized, which means it has to get its oxygen from the air, but that also means that anything in the air can get into your eyes and then eventually be a diffusion into your bloodstream.
So all you young ladies are far too young to be drinking, but when you get to that age, if you hold the alcohol in your mouth, it'll actually absorb through the top palate, and you can get schnockered in no